Hi everybody. So this time I have a case history, which is the Woodrow Wilson Bridge in Washington D.C., and then we'll come back and talk about soil classification. So let me get the lights, and then we'll talk about the case history. So the Woodrow Wilson Bridge, there is an old wooden Wilson Bridge that existed in Washington D.C., but in 2001 a new bridge was designed and opened in about 2006 because the old one was too small and larger traffic needed to be accommodated. And this case history is related to scour, erosion of the soil around the bridge pier. And you will see that scour is a big problem in our country. So these are the credits. And first of all, I want to talk about erosion. So the whole case history is related to erosion. Nothing fell down. This is not a failure case history, but I want to talk about erosion first. And you can see here on the left-hand side, or right-hand side first, this is Lake Ontario, Lake Erie, and the Niagara River runs from Lake Erie into Lake Ontario. And there's a big difference in elevation between the two lakes, and this is why we have Niagara Falls. The Niagara Falls started a long time ago, about 12,000 years ago. They were at the level of Lake Ontario, and they've been regressing by erosion all the way to about halfway between the two lakes right now, where they are today in the city of Niagara. You can see on the left-hand side the Horseshoe Falls. Maybe some of you have been there. In 1841 we're at this location, and in 2006 at this location. So there's a significant amount of erosion. This is rock erosion in this case, and the Niagara Falls have traveled about 11 kilometers of lateral erosion from Lake Ontario towards Lake Erie in 12,000 years at a rate of 0.1 millimeter per hour. And then if we go to the Grand Canyon, obviously a significant amount of erosion. You have a big hole in the ground, a 1,600 meter vertical erosion by the Colorado River in 10 million years in this case, or 0.00002 millimeter per hour. And if you looked at this number and you say, wow, this is negligible, well, in the process you would be neglecting the Grand Canyon. So it's not just a matter of the rate of erosion, but how long that rate of erosion is being applied. In this case, a very small rate of erosion over 10 million years sure makes a big hole in the ground. And I remember the first time I went to the Grand Canyon, I kept going up and up and up, and I said, wait a minute, this is a hole in the ground, and yet I'm climbing a mountain. And then it dawned on me that the Colorado River at the bottom of the Grand Canyon has to be at positive elevation so that it can actually go towards the ocean. And therefore, the Grand Canyon, actually those 1,600 meter high or deep hole is actually a mountain that's 1,600 meter high. And then I wondered, how is it possible for a river like the Colorado River to hit this mountain, 1,600 meter high mountain, and decide to go right through the center of the mountain and make this big hole and split it half on one side, half on the other. And then looking into it, the river was there first. And then the Grand Canyon was part of the Nevada Plateau that rose over a long period of time, those 10 million years, the plateau rose, and the river just kept cutting through it. So remember, the river was there first, and the plateau rose after that, and that's how the Grand Canyon was formed. And then you think about this simple process here. If your faucet drips on a pebble of rock for 20 million years, will there be a hole in the pebble? And of course, I don't know the answer, because that's a kind of a long time, long research project. I haven't found a PhD student who wants to stay around for 20 million years. Anyway, when I ask the question, most people say, yes, there will be a hole in the pebble. And then you wonder, and I would agree with that. It would seem to me that there would be a hole in the pebble. And then you wonder, how is it possible for water, a material that soft, to make a hole in a pebble, in a rock, a material that strong? And so we could, and I do think that cyclic loading has to be part of the answer. So anyway, back to the scour and bridges. You're looking here on the vertical axis to the number of failures, bridge failures, from 1966 to 2005. 1,500 failures. And then on the horizontal axis are the causes of the failures. And you can see that on the right-hand side, the big yellow bar is hydraulic and scour. Erosion. Collision is number 2, and earthquake is down at about something like about 2% or less. So scour is the number 1 killer of bridges. So we've started to work on this in our research a long time ago, about 30 years ago, and we developed this instrument where we take a Shelby tube. You can see the Shelby tube right here, and we push it through the bottom of a conduit where water is flowing. So the water is flowing all around. It's a closed circuit. It's flowing, and it's flowing on top of the Shelby tube here, and you can see the schematic. You have the soil in here, you have the water flowing in the tube, and then the piston is pushing the soil only as fast as it is being eroded by the water that flows over it. And so this allows us to make some measurements of how erodible soils are. And then one of the things that's very important, you know, we talked about soil classification. You have clay, silt, sand, gravel, riprap. And here, instead of the percent finer, I'm plotting the critical velocity. In other words, the velocity at which the erosion process is starting. And you can see that for the sand, gravel, riprap, it's increasing linearly because the larger the particle, the heavier it is. You know, I said that gravity forces and friction forces would govern the behavior of these large particles. But on the side of the silts and clays, the rule of gravity breaks down because the electrical and electromagnetic forces are taking over, and you have a lot more variability. So when it comes to scour, you can see the size of this person right here and the size of the hole. The water is flowing in this direction and making a hole because of the obstacle that the pier is representing. Here's in the Indian River Inlet in Delaware. The water is flowing back and forth due to the tides, and when it goes in this direction, you can see here the big hole that's created because the water is being contracted in the flow. So these big holes certainly can develop. All right, so let me take you to Washington, D.C. And this is the Woodrow Wilson Bridge, the old one. And we are right here in Washington, D.C. I took this picture as I was landing at Reagan Airport. You see the Washington Monument is here, the Capitol is here, the White House is here, and here is the Woodrow Wilson Bridge. This is the old bridge. So it's a bascule bridge to let the ship go by. And here is a rendition of the new bridge, much bigger. There are 6 lanes, both directions, and also a bascule bridge. And you can imagine that the piers, the bascule piers, are going to be massive. Here are the soil layers. We have soft clay for about 20 meters, and then hard clay below that, a little bit of sand. We're going to look at the main channel, not the secondary channel. So soft clay over hard clay. Here is the stratigraphy. That's the main channel. That's the secondary channel. The bascule piers will be in the main channel here. And here's the soft clay, and then the hard clay below that. Here are the bascule piers. You see the water level is here. Then the pile cap is here, and the piles are here. You can see the plan view with all the piles that are going to be set, driven in the river bottom to hold the bascule piers. So we went and got some samples at the site, brought them back to the lab at Texas A&M University, and tested the samples. We also simulated the flow. You can see here flow versus time. We simulated the flow that the river had generated over the last 40 years. And then we created the scour depth around these big bridge piers as a function of time. And it gave us about 8 to 10 meters of scour depth. So that's a, you know, a 3-story building. That's a big hole in the ground. Others that were involved as consultants created a simulated version of that bascule pier, but used sand. And as I mentioned to you, you had soft clay over stiff clay, but it's a lot easier to use sand in the lab to be able to measure the depth of the scour. And then in the end, we all got together, and there you see these are essentially different consultants, and here was Texas A&M University. So we were on the low side of the predictions. Most people predicted 20 meters of scour or more, and our prediction was around 10 or 11 meters of scour. And so there was a debate, why are you so low? And I said, well, I don't know. I've developed a methodology, and I tested the soil from the site. And I said, did you test the soil? Oh, no, we didn't test the soil. I said, well, you know, what did you assume? Well, we assumed it was sand, but it's clay. And so, you know, there was a big discussion here. In the end, they did assume 20 meters and built the bridge on that assumption. And you can see that the piles right here for the bascule piers are going down some 65 meters below the water level. And so these very large piles were load tested, static load test. There were some stat dynamic tests. Stat dynamic test is where you put a big mass on top of the pile and you shoot an explosive, you shoot the mass up, and by reaction the pile goes down. It's pretty impressive. And so here are the piles, and you can see the scour depth here. Here's the piles being driven. This is the old bridge right here, and this is 1/2 of the new bridge. I'm sitting, taking the picture on the other half, which was already constructed at that time. And these are the bascule pier. One of the things that was interesting, so at the time, the cost of the bridge between abutment, the project itself was $2 billion, but the cost of the bridge, because you have approach embankments and so on, but the bridge between abutments was $625 million. The cost of the foundation was $125 million, and I tried to convince the folks that were doing this, this work that, you know, if you're going to save 10 meters of pile, because I was predicting 10, all the others were predicting 20, that would be a saving of about $25 million on the foundation. Maybe we should instrument the river bottom to see if it's going to be 10 meters or 20 meters, and unfortunately that did not take place. All right, so that was the story about the Woodrow Wilson Bridge, and we continue to work on this bridge tower issue and making progress along with the folks on the Federal Highway, the Department of Transportation around the country. All right, let me put the lights back on and turn this off. Oops. Like this. And then we'll get back to, I hope you're enjoying those case histories. They give you a little bit of an idea of what geotechnical engineers work on, and we'll continue to do that unless I find that we're running out of time and we really need to concentrate on the topic. All right, so today I'm going to talk about soil classification. Let me write this here. And I'm going to use the unified soil classification system, USCS. So USCS is not United States Classification System, it's unified, so because it actually were used worldwide. It was developed around 1950 or so by the International Society, a committee of the International Society for Soil Mechanics and Geotechnical Engineering. And it's quite useful because you can go any country in the world and this system is known by everybody, and that means people can talk to each other and understand. We're going to aim to use two letters to classify the soil. So the first letter will be either G for gravel, S for sand, and silt is also S. So we had to use a different letter, and for silt we're going to use M, because I believe silt is miala in Swedish. All right, so that's where it comes from. And again, I believe the chair of the committee at the time was from Sweden, so he said, well, let's use it. So M for silt and C for clay. So that will be the first letter. So the first letter will tell you what is the dominant particle size for the soil. The second letter will be placed next to this, and it will be either P for poorly graded, W for well graded, and we are going to decide on whether it's P or W on the basis of coefficient of uniformity and coefficient of curvature. And then we're going to use M and C for silty or clay. And this will be for coarse-grained soils. these are the coarse-grained soils. The second letter for the fine-grained soil will be either an H for high plasticity, or an L for low plasticity. You see that in the case of the fine-grained soils, so this is for fine-grained soils. So we could end up with a material that is called an SP. So SP would be a poorly graded sand. So I mean, for example, you know, a uniform sand at the beach where all the grains are the same size. The coefficient of uniformity, coefficient of curvature would lead you to conclude that it would be poorly graded, and we will see in a minute how we make those decisions on S and P much more scientifically than by just looking at it. So this would be a poorly graded sand. If you had a GM, this is not General Motors, it's a silty gravel. So that means it's a gravel that has a fair amount of fines in it, or a dirty gravel. If you had a CH, this would be a high plasticity clay. Mount Marionite, for example, would be very likely a CH. And you could have maybe ML, which would be a low plasticity silt. So this is the typical outcome of a classification. And so if you talk to a geotechnical engineer from South Africa or India or Japan, and you tell them, well, I had a CH, then they'll understand what you're talking about, and then you can continue the conversation to geotechnical engineers. All right. The key question now is how we're going to make decisions on the first letter and the second letter. And there are two big parts to the USCS system. One is for the fine-grained soils, and one is for the coarse-grained soils. So let's look at the fine-grained soils first, because it's very simple. For the fine-grained soils, we're going to be using the Atterberg limits, and you remember the charts. So let me actually build the. So I'm on page 56. So on page 56, you'll see there are two flow charts, and we're going to decide, I'll put it in red here, so fine-grained soils, fine-grained soils will be those, will be those such that the majority of the soil particles are, so you have 50% or more, smaller than number 200. Okay? So if you find in your grain size distribution that 50% or more by weight of the particles are finer than number 200, then it will be a fine-grained soil. And the fine-grained soil means it's either going to be an M or a C as a first letter. And then as a second letter, it's going to be either H or L. How do we decide? Well, we go straight to the plasticity chart, the one I showed you last time. And this plasticity chart has the plasticity index here. And the liquid limit on the horizontal axis. Okay, so this goes from 0, I don't, let's see, in the book I went, 0 to 100. And the big separation is at 50. And then the plasticity index goes from 0 to 60 or 70. And then there is a separation that goes like this, and it goes all the way there. This is called the A line. Not sure what A, but that's how it is. And then you have plasticity index. So remember, plasticity index is WL minus WP. The liquid limit minus the plastic limit. And here you have the liquid limit, which is WL. You're going to get a classification problem in the midterm. All right, it's pretty given. So you already know that you're going to get a phase diagram problem, and you're going to get a classification problem. Many times I see mistakes because you would take here, instead of the plasticity index, you take the plastic limit. So it's not WP on this axis, it's WL minus WP. So if I give you the liquid limit and the plastic limit, first step is make the difference and then plot this in there versus the liquid limit. And then once you have done that, then you see where the coordinates of the material you have fall. If it's in here, then you're going to have a CL. If you're in here, you're going to have a CH. Why? Because the liquid limit is larger than 50, and that means you have high plasticity. If the plastic limit is, the liquid limit is less than 50, you have low plasticity. Here you will have an ML rather. So this will be low plasticity, ML, and then here will be MH. So when you're given, when you've made the decision that 50% or more is smaller than 200 by weight, then you go straight to the classification, to the plasticity chart, and you plot the point on there. So you might have a plasticity index that's like this, and you might have a liquid limit that's right here. So the point is here, and you say, okay, I have a CL, done. When it becomes a little bit more complicated is when you deal with coarse-grained soils. And I'm going to go back in here. And because the flow chart for coarse-grained soils is larger. But I'm also on page 56. So coarse-grained soils, as you can imagine, we're going to have here coarse-grained soils. These are soils where 50% or more is larger than sieve number 200. Okay? So you've looked at your distribution, your grain size distribution, and you find that you have more than 50% that's larger than C200. Let me put here a typical grain size distribution curve, because we're going to make use of that curve. So here you see the plasticity chart is what really governs the classification. For the coarse-grained soil, it's the grain size distribution curve. So remember, here we'll have the percent passing, or finite. This goes from 0 to 100, and then here we'll have the particle size in millimeters. And you remember it goes from 10 minus 4 to 10 to the plus 1. And then in here, we're going to have, so we'll have the gravel, the sand, the silt, and the clay. So clay, silt, sand, and gravel. So let's say that in here I have a curve, that a distribution curve that looks something like this. So the first thing I got to decide, I know it's a coarse-grained soil because I've looked at this and it falls in that category. The second step is it a sand or is it a gravel? Well, you can see that in this case, I've got this much sand from here to there. So this is the amount of sand, the percentage of sand that I have in the material, and then I have this much gravel. So this would be the sand percentage, this would be the gravel percentage, and these would be the fines. So it's clear in this case that that would be a sand, because you've got more sand than any other material. So we'll have to translate this into that decision box. So I wrote here sand, if the portion larger than number 4. So number 4 is right here, all right? This is sieve number 4. If the portion larger than sieve number 4 is less than 1/2 of the portion larger than 200. Okay, so that's the decision box for sand. So what that means is that here's number 4. The portion larger than number 4, so maybe, I don't know, 80% here, is less than 1/2 of the portion passing 200. Wait a minute, I made a mistake here. Number 4 is not here. This is number 200, because that's the separation. So this is number 200 right here. And this is number 4. Okay? So the portion larger than number 4, this one, is less than 1/2 of the portion passing number 200. I mean, you can check it this way, but I would suggest that you look at how much sand you have and how much gravel you have, and if you have more sand than gravel, then that means the classification should be a sand. Now, several cases regarding the portion passing 200 here. So first, if you have less than 5% passing 200, so if the portion if the portion, the percent smaller than number 200 is less than 5%. That will be one case. And then there will be another case for if the portion passing 200 is more than 12%. So that's another decision box. And then the one in between is if the portion smaller than number 200 is between 5% and 12%. So it's an intermediate case. So once you've seen that most of what you have is sand, then you look at the portion passing 200 and you say, is this less than 5%? Is it more than 12%? Or is it in between the two? If it's less than 5%, this is going to be a clean sand. There's not that many fines. If it was a dry sand and you let it fall on the table, then it would not make much of a cloud of dust. If you have more than 12%, this will be a dirty sand. And then we'll have to decide whether it's clay sand or silty sand. To make that decision, we're going to look at the coefficient of uniformity and the coefficient of curvature. So if C sub u is larger than 6 and C sub c is between 1 and 3. So you remember you've calculated your C sub u and C sub c from d60 over d10 and d30 squared over d60 d10. That gives you C sub u and C sub c. If they satisfy this, then your classification will be, let's see, yes, SW. So it's a well-graded sand. If you are in this category here, then that means you have a lot of fines, and then you go and look at the Atterberg limits, and oh, wait a minute, I have two, I'm sorry, I went too fast here. So you need to decide, you know it's a clean sand, but you need to decide between SW or SP. And so here, the first, we said C sub u larger than, what was it, 6? Yeah, larger than 6. And C sub c between 1 and 3. All right, that was our first box. And in this case, we concluded that it would be an SW, a well-graded sand. If we have a C sub u that is less than 6, and this one says and here, okay? C sub u larger than 6 and C sub c between 1 and 3. Here it's the contrary of this box. So the contrary of and is or, C sub u less than 6, or C sub c larger than 3, or C sub c less than 1. Okay, so that's your decision box here. And then in that case, the conclusion is we have a poorly graded sand. If you in the process, if you ended up in this box, in other words, you have a fair amount of fines, the percent passing 200, that number here is larger than 12%, then in that case, you use the Atterberg limits, and then you decide on that basis. So if you find that, so use PI and WL, because remember that's what we're using here, PI and WL. Use PI and WL, and if you're above, let's see, that first one is below the A line, all right. So the first one is below the A line. So use PI and WL below A line. So for some reason, you've plotted and you might have a point that goes in here, and you find that the point is here, let's say. So you're using the PI and WL, and in this case it comes here, below the A line, you're going to use the letter M. So in this case, let's see. So that's our decision box here, like that. And then the conclusion will be that we have an SM. So below the A line, we're going to use the M, and above the A line, we're going to use the C. So in the second box here, if you have, so PI and WL, and then above A line, then the conclusion is SC. And then if you find, sometimes you might have a point that falls in this hatch zone here. You may have coordinates that go like this, and then this is what we call the hatch zone. So if in hatched zone, then you have to use both symbols, because essentially you cannot decide. So you have to use SM-SC. Okay. And then if you find yourself in this box when you're between 5 and 12, then run case less than 5%, run case more than 12%, and use dual symbol. Okay? So when you're in between 5 and 12, then you have to, so here you're going to be using dual symbol, something that will look like this. So it could be SP, SM, or it could be SWSC, or it could be, you have to use both sides of the flow chart and end up with your dual symbol classification. If you are here, right here, then you will have gravel if the portion larger than number 4 is more than 1/2 the portion larger than number 200. Okay, but again, it would simply mean that you have a lot of gravel and a little bit of sand, so you would call the soil a gravel. And that's how it would be connected here. And then you have the 3 same boxes. These 3 boxes still apply. Less than 5%, between 5 and 12, and more than 12%. And then it would continue in there. I'm not going to go through this. I prefer to do some examples. So the best way to, and by the way, if you get a classification problem on the midterm, I would give you the classification chart, and I would give you this. Okay, you would have both of those things, so you don't have to remember this whole classification system. Let's do some problems, and we're going to do problem 4.8. Problem 4.8, page 57. And we're going to do soil S3 and S5. So S3 and S5. Let's start with S5. So S5 is a soil, and we've run a number of classification tests where sieve number 4, 100% goes through. Then sieve number 10, 97 goes through, 97%. Sieve number 40, 82. Sieve number 200, 70. Liquid limit 48, and plastic limit 34. Okay, that's what you're given. I would say very first thing you do, calculate the plasticity index. So PI, liquid limit minus, so PI is 14. The first check is whether you have 50% or more larger than number 200. So you look at 200 and you see 70% passing. So you have more than, more than 50% is passing 200. So you're in the fine-grained soils. Right? In other words, you've got a curve where more than, you've got 70% right here, so you have a lot more fine-grained soil than you have coarse-grained soil. So you know that S5 is fine-grained. And write those things down as you go through the thing, because if you don't write anything, but at the end you say CM, I can't give you partial credit because I didn't see your step recently. So fine-grained soil. If it's fine-grained soil, that's what was here before. We go directly to the plasticity chart. And in the plasticity chart, back here somewhere, then I have a 14 on the vertical axis and 48 on the horizontal axis. So 14 and 48, I'm below the A line, and so I end up with ML. Okay, so that's the classification for that one. Again, fine-grained soil, relatively easy. Then we're given S3. So let's do S3. And the numbers for S3 are 63, 56, 42, and 4. And then it's not possible to run the Atterberg limits. Okay? So you look at, you only have 4% passing 200. So you're in this case. There's only 4% passing 200. Most of it is in the coarse-grained soil. So you do have a coarse-grained soil. So in here you're going to say S3, coarse-grained. Then you have to decide whether it's a sand or a gravel. And the easiest way is to actually plot the grain size curve. But if you look at it here, sand is between number 200 and number 4. So how much sand do we have? 63 minus 4. So sand fraction is 63 minus 59%. And so therefore the gravel is going to be what's larger than 63 or 37. So you have more sand than gravel, therefore the first letter will be S. So you know you're in here. Then you're going to check these 3 boxes here. And you see that 200 is at 4. So that means you fit here. You plot the curve, you calculate your C sub U and C sub C, and you see whether you fit here or there, and you can conclude, in my case, my calculations indicated that I had an SP, because C sub U, let's see, C sub U was 32.7, and C sub C was 0.2 after I plotted the curve. So 32.7, that was higher than this, so therefore I fit here and I had an SP. Okay? So you have some other problems that you can practice with, but I will see you next time.